Hello class, this is Ms. Riggins with today's video on section 4.5, the number E. As you're watching the video, please remember to write down any important information, formulas, equations, examples, or any questions you may have. Feel free to pause, rewind, or even replay the video as often as you would like so that you can get a better understanding. After watching the video, don't forget to write down your summary of the video and then submit that via the online whisk the day before class. All right, let's begin. So we're going to start talking about, if you remember last video, we talked about compound interest. So let's say, for example, that I have $1 that I'm going to deposit in a bank account that's going to give me an annual percentage rate of 100% over n compounding periods a year. So basically, from what you know of compound interest, after 1 year, how do I determine how much is in that bank account? Well, using this formula. $1 is my deposit, 1 plus the interest rate, 100% over n, since I didn't tell you how many compounding periods there are a year, raised to the nth power times 1 because it's 1 year. So this is what it would look like. So if I wanted to consider and see how it would look like for different values of n, what would that equal? Let's take a look. Again, the $1 remains as the principal deposit, and the 100% is constant as well as the nominal interest rate. But let's take a look. So if I compound it once a year, then after 1 year, my approximate balance will be $2. And you can figure that out by just plugging in 1 for these n values. If n is 2, semi-annually, my approximate balance will be $2.25. If n is quarterly, it will be $2.44. If n is monthly, which is 12, then it will be $2.61. And if it's daily, it's $2.71. So the question is, what if I increase it to beyond daily? In other words, let n be something more than $365. Let's see what that will end up with. Let's say it's hourly, which means it will be compounded every hour, which is there's 8,760 hours in a year. So my approximate balance will end up being 2.718. So it looks like even though we made a big jump from 365 to 8,760, it looks like our approximate balance ends up hovering around 2.71 something, maybe even 2.72. Let's do it for every minute of the year. So that's 525,600 minutes. And we end up with the approximate balance of 2.718279. And as you can test these values and plug in n for each of these numbers, you will get these exact balances. So it seems like it hovers around 2.718, or definitely no more than 2.72. Let's try for each second. We still get something that hovers around 2.72. So what's the significance of that number? Well, that's a very popular number. And that number we call E. And it's a very popular constant, and it's around 2.718, as we saw. And we call it, if we let E be the base of an exponential function, we call it the natural base. But anyway, this E is, and we're going to use it a lot. Instead of keep on writing 2.718, 2.718, we just write E. So let's take a look at the various exponential functions with different bases. Here's a base of 2, here's a base of 3, here's a base of 10. And E is going to fall somewhere in between the base of 2 and 3 because E is around 2.71 or 2.718 or 2.7181, whatever the deal may be. So somewhere in the middle is our E. So the question is, let's say I had a value B, which is another base, which is greater than 0. And the question is, how can I write B in terms of E? I know some of you are like, well, why would we care? But trust me, it's going to be important a little bit later. So for example, here's my B, somewhere on the y-axis is greater than 0. And because the range of this exponential function is all positive numbers, there's going to be some k value. In this case, it's going to be right here, where if I plug e to the k, I'm going to get out b. And even if I were to change where b is on the y-axis, as long as it's positive, I can always find a k in this case here, such if I plug in e to the k, I'm going to get out b. So in other words, there exists a k where b is equal to e to the k. And k can be any number, positive or negative, because as you can see here, if I made b somewhere over here, it intersects the graph somewhere over here where k is a negative number. Why is that important? Well, k, since e is the natural base, then k is related to the natural base in a special way. I'm going to show you this important thing. K is called the continuous growth rate of any exponential function of the form q is equal to a times b to the t. And that means that k is what e to the k needs to be to give me that value b. And why is this important? We're going to look at an example about why this is important, but it's important to know that whenever you see the word or phrase continuous growth rate, then that means e to the k is going to give you the b that they were talking about, and vice versa, okay? Or e to the k is going to allow you to compute what b is. So we have a way of taking a general exponential function and changing it into an exponential function with the natural base of e. That's very important. Now let's take a look at an example. This is from your textbook. Caffeine leaves the body at a continuous rate of 17% per hour. So that should be a hint. Continuous rate of 17% per hour. How much caffeine is left in the body 8 hours after drinking a cup of coffee containing 100 milligrams of caffeine? Well, because we saw the word continuous rate of 17%, that means we can write the exponential expression as a is equal to 100 times e to the negative 0.17t. Now, of course, the question is, first of all, where did the 100 come from? Well, if you recall, the cup originally contained 100 milligrams of caffeine, okay? So if we drink all of it, then that means initially our body will have 100 grams of caffeine. So that's our starting value. And then it says caffeine leaves the body at a continuous rate of 17%, which means that there's a decrease of the amount of value, which is why we have k here being negative 0.17 instead of just 0.17. Now, if we were adding caffeine at a continuous rate of 17% per hour, then the k would be positive 17. But because it's leaving the body, we originally have 100 grams of caffeine in the body, and then it's leaving the body at 17%. That's why it's negative 0.17t. Okay? So the question is, after 8 hours, how much caffeine is left in the body? Well, since t represents hours, since that's the continuous rate per hour, then all I need to do to answer this question is plug in 8 for t and get my answer. And my answer is 25.67. Interesting, huh? Now, some of you may be asking, well, what's the difference between the continuous rate that we just learned about and the annual interest rate that we talked about last video? And that's a very good question. So let's take a look at an example. So say, for example, that I have my interest is growing at an annual rate of 7.7%, which means that if P naught is my initial balance, then that means that I can express that relationship as P naught times 1.07 to the T, because we're compounding it, let's say, annually. Okay, so how is that different from continuous growth rate? Well, continuous growth rate is a little bit different because instead of a base of 1.07, if it's continuous growth rate, that means our base is going to be E, and that is going to be raised to some K power. And our K power is going to be 0.07, of course, times T being the number of years. And so that's the difference between the two. It's based off the base. And then, of course, the exponent of the base. So annual means just a different base of 1 point something or less than 1 if it's decay. Continuous growth rate means that the base is going to be E, and the power is going to involve your interest rate, R. Okay? All right, so let's take a look at another example. If you remember in the beginning of the video, we talked about 100% nominal interest rate. Let's take a look at just a 6% nominal interest rate, and let's see what happens when we change the amount of compounding periods a year, and see what happens. So if our compounding frequency changes, how is that going to affect the annual growth factor and the effective annual rate? So if it's annual, our annual growth factor is going to look like 1.06 something, and the effective annual rate is 6%. But then as we increase the compounding period to monthly, our annual growth factor is now 1.0616778. So the effective annual rate is 6.16778. Hope you're seeing a pattern. Daily, this is the result. Hourly, that is the result. So the question is, if I keep on increasing the compounding period after hourly, if I do minutes, if I do every second, what do you think the annual growth factor or the effective annual rate is going to be? Well, if I do it continuously, that means that the annual growth rate is going to kind of limit out at 1.0618365, i.e. the effective annual rate is 6.18365%. Well, where do we get this number from? How can we compute that without having to keep on testing different values? Well, that's easy. What we're going to do is, if I were to plug this into the calculator and try and see what K value gives me an annual growth rate of 1.061835, I get e to the 0.06, and you can test that out on your calculator as well. If I were to plug in the nominal rate for the exponential, for the base function, if I were to plug in the nominal rate as the exponent for the natural base, then I will get the annual growth factor rate, and from that, subtract 1 and divide by 100 to get the effective annual rate. So we have a theorem here which says if interest on an initial deposit P is compounded continuously, so the growth factor rate, continuous growth rate is K, at a nominal rate of R per year, the balance can be computed by using the formula B is equal to P times E to the RT. So in our example, our R was 6% because that was our nominal rate, so that means our R was 0.06. And that's how we ended up with our value if we were to compound it continuously in T years. All right, that's it. Please take a look at the examples in the book as well as the problems in the chapter. All right, let's go. That's it.